is quadratic. Okay? So basically, I have something that looks of the following form. So I have some product over, exn. Okay, and I'm going to take the liberty of making these integrals from minus infinity to infinity, because otherwise it doesn't help to have a Gaussian integral, right? If you have finite limits, it's just dead. So let's just make it minus infinity to infinity. So what justifies that? Well, imagine that I have coarse-grained this over some very large region. Let's say a region which has 10,000 spins. Okay, so the limits of this field are really plus to minus 10,000. And as long as the width of this Gaussian is not too large, I should be okay extending the limits. Okay, the error I make is exponentially small.
Which integral you are writing like this? That S of phi. Okay, S of phi you are writing.
I'm going to write an integral that's a true statement, and then we will apply it to this.
Okay.
Okay? So this is just some n variables. I don't even tell you how many of them there are.
Oh, okay.
Okay? So now I want to do an integral, okay, of a Gaussian. So this Gaussian will look something like this. So it will look like xi, so 1/2 xi, so let's call it mij xj, okay, minus or plus, it doesn't matter, okay, hk xk, okay. Now every repeated index is being summed. Okay, so I'm using the summation convention. So this is some matrix, so you can write it as x transpose, if I want to think of x as a column vector, x transpose mx. Okay, and this is h transpose x. Okay, so now I want to do this integral. This is a Gaussian integral, right? So you should be able to do it. So how do you do a Gaussian integral like this? It's very easy. All you do is you diagonalize this end, right? And then you get some eigenvalues. Let me call it mu a. Okay? So these are the eigenvalues for that. So once you diagonalize it, you can write it in terms of what I call normal coordinates, right, of this matrix. And each of them will be its own Gaussian, right? And then you can do that integral, and that will give you basically the square root, the product over all n, or k in this case, right? The square root of pi over mu a, right? This is the result of doing the Gaussian integral. And then there's this stuff here, right? So this you can always do by completing the squares, by shifting x and completing the squares, right? So the result of this is going to be e to the power plus 1/2 h transpose m inverse h. Okay? You guys believe me? You don't have to believe me, you can just check. It's very easy to check. Okay? The advantage of having an h here is that now I can take derivatives with respect to various different h's and get all kinds of correlation functions. Okay? For example, suppose I want the correlation function of, let's say, x1, x217, right? In this particular action. How do I get that? So I say this is going to look like 1 over g times integral the product of all these xn's, right? Product over all these xn's. And then you have this stuff here. I should really multiply by x1 times x217, right? But instead, I can rewrite it as b squared d h1 d h217. Okay, you agree with that? Okay. Now, of course, I can take this thing out, right? And I can rewrite this as right? Very good. I don't even actually have to do that. Really, all I need to do is, supposing I do the integral now, it gives me this result, right? Now I look at where the h dependence is. H dependence is sitting here, right? So it's very obvious that the result of all this stuff is going to be M inverse the matrix element 1, 272. Right? So the correlation function of these x's is basically nothing but that particular element of the inverse matrix.
So,
Yeah.
the pi over square root of pi over mu a, this mu a also depends on h, right? Because when you diagonalize the exponential, there is a
absolutely
h,
not.
x and m also.
No.
So you have to
The
copy
mu
this
depends only
square.
on this side.
Yeah.
It doesn't depend on h.
No, but when you make a complete square, with the m there will be some factor of h also, some addition will be
No.
there.
The point is that so let's complete the square here, right? So what will this be? So this, I'm just going to write this part here, right? I'm going to write it as minus 1/2 x transpose minus h transpose. Or maybe I put it, yeah. Okay? And then m x minus h. Not quite. H transpose m inverse m x minus m inverse h. Okay? And now you know that what is missing here, that is just and now I just shift my variables. And that nothing to do with the idea. Okay? Good? Alright, so now what I gotta do is, once I've set lambda equal to 0, this guy looks quadratic in all these fields. Okay, so what I gotta do is diagonalize that quadratic form. Okay? So let's see what the quadratic form is. So let me make everything finite. Okay, so that I don't have any infinities in there. Okay, I'll put the system into a big box. Okay, a cubic box of size L on every side. So I have d to the dx 1/2 grad phi of x squared plus r over 2, let me call it n squared. Okay? Again, this is notation from quantum field theory. It's very useful. Okay, so we'll just use that notation. Okay, so this action is translation invariant.
You are not writing that each term.
I'm not writing the h term.
Okay.
Because the h term I needed only to compute the correlation function.
Okay.
But now I know that the correlation function in general is just going to look like m inverse. Okay, so all I need is really m to get the correlation. Okay? Good? Alright. The m is this guy here, this matrix that's acting upon phi. So in order to really make it look like a matrix, I'm going to take a Fourier transform, because that will automatically diagonalize this. Anything that's translation invariant, you take a Fourier transform, it at least partially, most of the way, diagonalizes the object in question. Okay? So let me define for you the Fourier transform. So I will say phi of x is the sum over k, okay, e to the I k dot x over L to the d over 2 times phi tilde of k. This is the Fourier transform. Okay? These k's are discrete because I'm putting periodic boundary conditions, and therefore each of my k's is actually, the splitting is 2 pi over L, and there's some first integer, second integer, and so on, and the dth integer over here. Okay? That's what it is. So it's a sum. Alright, and of course the inverse transform, you can do it very easily. It looks exactly the same, except now there's an integral. Alright? Okay. So now all I'm going to do is I'm going to plug this in over here, and I'll see what I get. Okay, so what is grad phi? Grad phi is just right. So I want to do grad phi squared, 1/2. So integral d to the dx, 1/2 grad phi dot grad phi is going to be equal to 1/2 to the d sum over k1 and k2 right? Okay. Maybe this is all obvious. Maybe I should just skip all this in. To how many people is this completely obvious, what I'm going to do? To how many people is it not completely obvious? Okay. All right. So now you see these k's, they have particular quantized values, right? And now I want to integrate over this box with periodic boundary conditions. And clearly the only guy that survives here, this integral, all the x dependence is contained in this integral. The only thing that survives here, this integral will give me an L to the d stands a delta of k1 plus k2 over 0. This is a collector delta. Everything is discrete. Okay? Otherwise, it's the sum of a complex unimodular periodic function that goes through all its possible values on the unit circle, and therefore its integration is 0.
Sir, there is a minus sign that you have written that.
There is no minus sign. This is a dash.
Sorry,
It's a dash, it's not a minus sign.
sorry.
Okay. All right. So this tells you that k2 is equal to minus k1. Okay? And it cancels the power of it. So in fact, this thing is really simple. It's just the sum over a single k. So it's phi tilde of k, phi tilde of minus k, k squared. Okay? Good enough?
But you kind of took a finite size lax, right? So this way of doing the derivative, like you're doing continuous derivative kind of thing. So
No.
there is
X is continuous. My x is now